So my name is Yue Li. I'm a co-founder, CTO of MemVerge. So today I'm going to just give you another update on our memory machines, basic latest development. But before getting into the details, I would like just to describe a little bit on the Intel Optane DC persistent memory, just in case you are not familiar with it. So if you haven't seen this before, it actually looks like this kind of DIMM form factor, the stick. Right? It's a DIMM and goes to the DIMM DDR4 slots right next to the DRAM DIMMs and right next to the CPU. So that's why it actually can guarantee a DRAM-like performance because it's very close to the CPU. So specifically, a persistent memory provides three configurations. It starts with 128 gigabyte per DIMM and goes up to 512 gigabyte. So it provides a huge capacity per DIMM. And today with Ice Lake CPUs, you can basically support up to 4 terabyte memory PMEM capacity per CPU socket. So if you have a two socket servers, you can easily go up to 8 terabyte PMEM capacity. So more importantly, also it's a much less costly than DRAM, especially this year, DRAM's price increases a lot, but persistent memory's price still stays stable. So that gives you even more advantage on the cost side. So the persistent memory actually has a very good performance. It offers about roughly 300 nanoseconds access latency. So it's a bit slower than the DDR4, but if you look at the numbers offered by NVMe SSDs, it's basically orders of magnitudes faster than the SSDs. And most importantly, it's also persistent if you use in a correct mode and if you use software like our memory machine to persist the data. So what is the motivation of a memory machine? And why do we want to build such a complex system? Right? So the main motivations come from the observation that we saw that the basic infrastructures for modern compute workload, such as machine learning and data analytics, they require more and more memory. So just to give you some data points here. So the latest, the very powerful GPT-3, which is a model, machine learning AI model for natural language processing, has 175 billion parameters. That accounts for more than 700 gigabyte size in memory. And during the training, it required batch sizes like 3.2 million of records. Think about how much memory that will take to fit all of these in the memory buffer to stream into the GPU or the CPU, right? So if you look at bioinformatics, the latest generation of genome assembly technology, the de novo genome assembly pipelines typically requires more than 512 gigabyte RAM for some non-human data sets, right? For plants, for bacteria, and so on. So the motivation for our memory machine is really, really simple. We want to supply infinite, very inexpensive, big memory to the memory-hungry applications. And we're hoping that those applications can fit all their data inside the memory so that it introduce less I/O to and from the disk, thus give a better performance. On the other side, we can replace much DRAM with lots of PMEM so that to reduce the cost. And also the servers now has more memory to use. So you can actually use less servers perhaps to do the same work that they used to need many servers before. So that server consolidation can also provide higher density and a lower cost. So here is basically an overview, a brief introduction on how memory machine works. So at the top, we have the applications that we want to support to run a memory machine. And these applications are typically memory hungry, such as in-memory database like Redis, Memcached, Hazelcast, like machine learning applications based on PyTorch, TensorFlow, the server virtualization based on KVM, Qimo KVM, and all these applications, the modern applications that they want to run inside the containers. So actually our latest release actually started supporting container deployment as well. So underneath, we have the hardware, the CPU, DRAM, and persistent memory. So how do we connect these two layers together, right? So first of all, we need definitely a memory machine works with so far we only works with Linux. So and the Linux with the persistent memory support, more specifically the DAX driver support. And with that, you'll be able to basically abstract those PMEM resources and DRAM resources into system DRAM and a bunch of PMEM devices. So that's actually means that we're using app direct mode. So with these resources, we build our memory machine, and we have a memory engine, which is the core of our data path that essentially create a software-defined memory pool that basically virtualizes the DRAM resources and the PMEM devices. And then inside the pool, there are many memory objects, and these memory objects will be directly mapped to the user space applications. And together with an application, with a memory allocator client library, which we call Transparent Memory Service, that offering the malloc and map interfaces, these libraries will basically map the memory objects into the user space, and does the sub-allocation for the application. So that application's memory allocation request will be redirected to memory machine to leverage all the memory we manage. So to be more specifically, memory machines offer a tiered memory allocation model. So by tiered memory hierarchy, I mean that the application sees the total memory capacity that equals the DRAM capacity plus the PMEM capacity. And also, our memory machine monitors the memory access patterns and trying to basically put all the hard pages and hard access into the DRAM and put very cold access to the persistent memory to still offer a better performance. Meanwhile, because we're using DRAM and PMEM, we also offer the users option to actually allow.
Could you go back to this prior slide, the full build out?
Yes.
So I always thought it was just a memory replacement completely, but there's actually memory objects that you're allocating in the memory space, let's say, and you're somehow providing some mapping from those memory objects to real memory space for these applications. Is this how it works?
Yes, essentially, basically, it's kind of like the object is kind of like a huge space, basically given to each application. So each application, basically, you can think of each application will have a separate object, but it's kind of like a large memory space, concept memory space to use. Then with our allocator, essentially, it does actually sub-allocation from basically carve out little pieces from this big object to basically to allocate for those data structures the application allocates.
And so you're using sort of virtual memory kind of page space for that to map to real memory, real mem machine memory, or is that what you're doing?
Exactly. So we are backing the virtual memory address space used by the application, either through using the PMEM we manage or using the DRAM we manage. So the decision is based on the temperature of the page.
Yeah. So the one thing that seems to be missing here is SAP HANA. Is that something that's coming, or?
That's actually basic. I would say it's a work in progress. Today we don't officially support SAP HANA.
Okay, thanks.
All right. So with this basic allocation model, user can through the user configuration file, you can basically launch the application with different DRAM PMEM ratio, to satisfy different cost and performance need. For example, if you really have an application that you don't care about performance, just want to use it for testing, right? You can just give the PMEM to that to save the cost and yield the DRAM resource, expensive DRAM resource to other more performance-driven applications, right? Or if you have a performance-critical application, you can increase the DRAM PMEM ratio so that actually it can run faster than the running only on PMEM. So any questions? Okay, so today, this memory allocation model only supports the local DRAM and the local PMEM. So tomorrow, we'll be able to support the remote memory, so which memories in another remote device sitting in another host. So this is provided guaranteed by the low latency, high bandwidth interfaces such as CXL and also the protocols like RDMA. So I want to show you two use cases for the transparent memory services. So the first one is a fast in-memory image recognition framework we built in a customer proof of concept. So in this project, we show that the memory machine allows orders of magnitudes lower latency than the baseline framework that uses DRAM and storage. So basically, what I show here is a baseline implementation is what customer has been using in production. So essentially, the core part, the central part, is the inference engine that embeds lots of algorithms, essentially that takes in a picture and trying to look for the most similar pictures, the candidates in a database. And all those pictures initially sits in the MongoDB, living on SSDs. So to accelerate that, they implemented a cache, a hash table inside the DRAM. And when when inference engine is trying to do the search, it will first trying to search for the hard data in the DRAM cache. Upon there's a cache miss, it basically will start consulting the MongoDB. And that's basically introduces the cache miss penalty. Essentially, you have to use a very slow IPC to contact MongoDB, and MongoDB needs to do deserialization, and read out the data from the disk and return that back to the inference engine. So the cache miss penalty is very, very expensive. So working with the customer, so we created basically another basic framework. Essentially, what we did is very simple. We just use the PMEM, give them our allocation library, and the customer is able to actually create another hash table inside the persistent memory and trying to actually move all the data in MongoDB into the persistent memory as well. So in this case, actually, not only the cache miss penalty is much smaller because we are just directly hitting the PMEM, and we're also getting rid of basically the serialization, deserialization, because here, now all the data actually are living in their native in-memory data structure format. So there's no serialization, deserialization gets involved. So as a result, we basically increase the throughput and latency significantly. So for example, in this figure, the x-axis basically shows the concurrency of the query, of the client queries. So the higher, that means that there's a more client that query the pictures at the same time. The y-axis corresponds to the throughput and latency. So if you look at the latency-wise, so the blue bars represents the latency of the baseline system based on the storage and the DRAM. And the right hand, the orange bars correspond to our performance. And you can see that the latency is basically several orders magnitudes lower. This is just because basically everything goes into the memory, and there's no disk I/O and no networking.
Right. So this is more of like an image search kind of solution. It doesn't seem like an image recognition AI type of solution here. So but yeah, I understand if you can bring the whole thing into PMEM, then you have instantaneous access and higher throughput on that image search kind of thing.
Yes, it's a part of the image recognition pipeline. They also need to recognize who this person is, what this person sort of like belongs to.
Oh, so it's part of the ML ops pipeline. I got you.
Yeah. Yes. Okay. So the next use case is on the same for transparent memory surface we recently developed. Is for the virtualized servers. So in this use case, in this testing, basically we are running, in this particular test, we are running multiple Qimo KVMs on memory machine. And those Qimo KVM supply the memory actually through the memories managed by us. So in this particular test, we run 9 VMs here, and each VMs run a MySQL database inside. And we also launch a separate, nine separate Sysbench benchmarking tool to stress the MySQL database in parallel. And what I plot on the right-hand side is basically the aggregated TPS transaction per second for all these nine MySQL servers. Okay, so you can see that we actually, in this picture, there are two categories, there are two clusters, right? The cluster on the left-hand side is the data, is a performance generated from a DRAM-only server. The DRAM server contains 784 gigabyte total DRAM capacity. So essentially that's 24 32 gigabyte DIMM sticks. On the right-hand side, it's basically is a persistent memory server that has 192 gigabyte DRAM plus 1.5 terabyte PMEM. And note that these two configurations actually have exactly the same hardware cost. Okay, so the exact same hardware cost, the same CPU but different memory configuration with the same cost. Because we can have a larger PMEM capacity because PMEM is cheaper than DRAM. So you can see there are two colors here. One is the blue one, the other one is orange. So these represent two testing configuration. One is using 8 threads per Sysbench, and the other one is 12 threads per Sysbench. So and you can see that On the left-hand side, each VM has 80 gigabyte memory, and among the 80 gigabyte, 60 gigabyte of each VM is allocated for the MySQL to use as a page buffer pool. On the right-hand side, because we have more memory to use, now we actually allow each VM can now have 160 gigabyte memory, and among this 160, 120 is given to the MySQL database to use as a buffer pool. So as a result, because of MySQL now living on memory machine now have more memory to use, now we show that actually for both testing cases, we can achieve up to 29% improvement on the transaction per second. This is just because the more memory, bigger memory brings more performance to the MySQL databases. Okay. So that's the two of the many use cases for the transparent memory service. So with application running on us, essentially you can use lots of memories, right? But however, we also recognize that with increased memory footprint, it definitely presents lots of interesting challenges. Let me show you a few. So first of all, if your application uses lots of memories, right? So it actually, when you want to, just imagine when you want to save the application states, it will take a long time to actually stream those huge memory states back to the disk. So for one example is an in-memory database. If you look at Redis or other databases like Memcached or Hazelcast, it will take a long, if you use terabytes of memory for the database, it will take long time, very long time to actually write to the disk. And also take a long time, when you want to restart, it will take a long time to reload back from the disk. So which basically is a long time to go to the disk and long time to read from the disk, okay? So also, even if you want to do an in-memory copy, say that you want to actually start a replica of your in-memory database for load balancing. So that in-memory copy is also very expensive. You have to, stream that in-memory states to a different process and recreate that process in that memory. So it involves networking, involves writing to another piece of memory. If it's 4 terabytes of memory, that will also take a long time to finish. So we observing these challenges, basically we developed the Zero IO snapshot technology, which is one of the enterprise data services offered by Memory Machine. So basically these snapshot services can basically persist the memory states instantaneously inside the PMEM, so that you no longer need to actually do the serialization and deserialization between the disk and memory and write to the disk. And you can also, with the snapshot living inside persistent memory, you can recover that immediately, right? Just because that memory state actually lives in the native format, you actually don't need to do serialization and deserialization, and you can recover that instantaneously from within the PMEM.
Yeah. So the snapshot, you say instantly in PMEM. So within like 90 nanoseconds, some kind of time frame, you could snapshot, a terabyte of memory or something like that. Is that what you're saying?
Yeah.
Or is it actually doing a mem copy from memory to PMEM into a different location?
Right. I will explain the next. But basically, if you only use PMEM, snapshot and PMEM basically takes about the tens of milliseconds to hundreds of milliseconds, but not like 99 nanoseconds. Yeah, but it's a hundreds, tens of millisecond level.
And you're actually physically cloning or copying the memory. You're not creating some sort of virtualized map into that memory space where you're keeping deltas and that sort of stuff.
Well, actually, I will cover that in the next slide, but we're not copying the memory. But I will go to the details. Yes. And also the snapshot actually can be, it's like a storage snapshot. You can actually clone the snapshot without actually doing the memory copies. So that allows you to actually copy the memory, sort of like the quote unquote copy the memory instantaneously. And these can all be done for the application without actually letting the application to be modified. So that's another benefit.
So here's a question. Does this introduce any latency while the snapshot is being taken?
Definitely, yeah. Just like a storage snapshot, we also have a mechanism to actually need to query down the application a little bit so that we make sure the data is in memory is consistent. Yeah. But that's also at the level of tens of milliseconds or hundreds of microsecond level. Yeah.
So can you use those clones and move a clone to a different machine so you can do, for example, database HA or so?
I'm not sure about database. We haven't really basically have a solution for database HA using clone, but yeah, we can actually move a clone to other nodes and restore from other nodes.
Will you show any of that in relation to things like Spark and being able to train across distributed clusters?
So yeah, actually Spark actually runs on us also. Yeah, Spark can use our memory, but today we don't support the snapshotting the Spark processes. Yeah.
You on that basis, it seems to me, and correct me if I'm wrong, that you could basically in a memory spread across multiple machines do memory coherency across them or cache coherency. Would that be an accurate assessment?
So today, actually, as I mentioned, we don't support the remote memory. So all the memory actually are local.
Okay.
Yeah. So that's that part, the coherency part between the nodes is not there yet.
So in a multi-system or multi-CPU, multi-node type of system where it is one physical machine where you're sharing memory, could you essentially in different memory pools in that system maintain a cache coherency?
So today the memory we offer is actually it's more like a private memory. It's actually the memory allocated only exclusively for that process. So there's no sharing between different applications. We're not using those malloc and mmap to share the memory. So we kind of like that. That's what we focus on right now. So it's like a private memory, no sharing. So we don't need a coherency between the processes.
Got it.
So what's the distinction between a snapshot and a clone of a memory space? Is it one's read-writable, the clone's rewritable, and the snapshot is just readable?
So a clone, we call it a clone. Correspond to the application instance. The snapshot is basically referred to the memory states. So when we do a clone,
okay. So it's an application specific. You're cloning, you're replicating the application and the data.
Exactly. So we're cloning the application. It's a clone of the application. So based on from the same snapshot. So exactly how does a zero-IO snapshot fits in the memory machine? Right. So we already show you this is the overview for the system. So essentially, as you know, that we have a transparent memory service that actually allocates memory for the application, so that we actually know that the memory location, the physical memory locations for each virtual memory address is used by different application. So with that information, right, when we want to take a snapshot, so we create the zero-IO snapshot component. That first, when we want to take a snapshot, we send RPCs to our transparent memory service to learn what are the memory locations that this particular application is using. Then the zero-IO snapshot component will send another RPC to our memory engine to ask a memory engine to use our snapshot implementation algorithm to actually snapshot the corresponding memory objects that backing those memory locations for different applications. And we have an internal implementation of the snapshot, which I'll cover in the next, to basically to support this kind of incremental based snapshots.
And the snapshot is API driven or console driven, or I mean, how do you say I want to snapshot my in-memory Redis database?
Yeah, that's a good question. So we offer like at least 3 interfaces. Well, the first two is like you can do it using REST API to say, okay, this is the process I want to snapshot. Just use the REST API to snapshot that. Or you can use our command line tool to basically passing the process IDs. Then we can snapshot that. Or for advanced power users, they can use our programming APIs to snapshot the particular memory regions they want to snapshot. So let me introduce more detailed feature of the snapshot. So first of all, the snapshot is instant. So by that I mean that the snapshot, when we take the snapshot, we don't really need to copy the in-memory data, in-memory state of the application to the storage. So there's no data movement or I/O required for that for the disk. And as I mentioned, we have a tiered memory allocation, which means that for application we'll use the DRAM to accelerate the PMEM. So there will be part of states inside the DRAM. So when we take a snapshot, we'll make sure that we'll flush the DRAM tier into the PMEM for persistence purpose. Also for data consistency purposes, we know that there's a CPU cache also is backed by the persistent memory. So we're also, during the snapshot, we'll also persist actually flush all the CPU cache back to the PMEM as well. And also notice that this very similar to the storage snapshot, right? We have, once the snapshot is taken, it's actually become the memory states managed by that snapshot is actually read-only, right? Then you might wonder, okay, how do you handle the incoming? The application is still alive and still updating the memory. So how do you handle the incoming memory updates? So we handle this. So there is really no secret here, because for storage industry, this technique has been already been widely used called copy on write. So this means that if there's incoming updates to a memory region that managed by snapshot, we'll actually perform copy on write. We'll see that which pages you're modifying, and we'll make a copy of that page, and also only record the delta, the changes into that the new copy. And we'll basically point our metadata point to that new copy, so that when you are actually reading the data, you'll actually read out from the newly copied the memory pages. And you can, of course, you can take another snapshot. Another snapshot will only persist the delta, the pages of the newly generated page we copied. And you can say that, let's say that you take another snapshot one, and you can do further updates. The further update will trigger more copy on writes also, then we can take another snapshot. Okay. So I want to just mention a few use cases here. So the first use case is basically, as I mentioned, we can with the snapshot capability, we can restore a large in-memory databases within less than 1 second. So what I show here on the left-hand side is the time it takes to restart Redis database that uses 300 gigabyte memory. That is basically represents 300 million key value pairs inside. Right. So for this database, the database initially, the database storage, their conventional snapshot sits on the SSDs. And when we load this back, we found that it takes about 15 minutes for the database to finish loading, to start serving the user. And for us, so what we did is that when we loaded the database, we take a snapshot, and then we shut the database down, and we restore the snapshot from our memory machine snapshot. We said it only takes about 581 milliseconds to finish, and you can see the database comes back, and you can start serving the users.
Does the application have to be aware of the presence of PMEM in order to really take advantage of this? Or is this transparent to the app, or it doesn't have to be built for PMEM properly?
Right. So this application is actually does not need to be aware and does not need to be modified to use our snapshot. And actually, our software also works for DRAM only situation. If you don't have PMEM, it's fine as well. It's just that we have to somehow export the snapshot to the storage so that you don't lose the snapshot when you reboot the server.
You solve a significant Optane problem. If you're running a database in memory and power goes out, and generally with Optane, you can actually corrupt your database even though it's persistent memory. Mm-hmm. And so with your snapshot, you actually eliminate that issue.
That's correct. So when we take a snapshot, it's always at a consistent point. So yeah, we can. That's how we can use the persistent memory to recover the database. Yeah. Okay. So then I want to mention another actually very interesting realistic use cases that we work with work on with a customer. So this is related to solutions to the expensive crashes in the media and entertainment industry software. So, but in that industry, the 3D graphics design software is widely used, by virtual effect companies or animation studios, right? And unfortunately, those software they crashes. Right? This could be due to multiple reasons, such as unstable in-house plugins. So they develop lots of the in-house plugins that are not stable, right? That can cause or system failures or hardware resource constraints. And these workloads are actually very GPU heavy. Most all these kind of applications, Autodesk Maya, Houdini, or Nuke, they all use GPUs in one way or another. And once there's a crash happens in production, the recovery really takes a long time to finish. This is simply because if you think about the movies, right, those movie scenes, right, they have to to recover those applications. They have to reload all this data from a remote storage server, stream them into this local server's memory. And those data are huge. And also that's the only part of the overhead. The other overhead is also the application itself has to understand the incoming data and trying to reinterpret those data into these pictures. Right? So that also takes a long time. So as a result, this introduced a much higher cost and the lower productivity to those movie animation studios. And this is just simply because the artist, once there's a crash, the artist cannot continue working, have to stop and waiting for the recovery, and their hour rate is very high. And as a result, the production schedule may be delayed. So here's actually the actual quote from one of our customers. So he said, the movie scenes can sometimes take 45 minutes to an hour to load. And if a system crashes, then they lose that work, and they refers to the artist, and the artist will lose their state of mind and the flow they were in. So it can take half a day or to recover, and that can be catastrophic to the artist and the production timelines. So that's basically the pain point. And here's basically how our snapshot can solve this. So essentially, I want to share with you some of the experiment results we did, and with some public available data sets. So the experiment we did is with Autodesk Maya 2020, and we test this our snapshot performance, recovery performance, using a widely available public data set called the Moana Island scene. So this is actually, if you are familiar with the Moana, the animation movie by Disney, so that's the data set, the island for that movie. So it's a huge data set. And then basically you can see that this is actually what I show on the left-hand side is actually a model, a tree model, actually in the Moana movie. So just one tree. So but the whole data set is the whole data set covers the very big island, including the volcanoes, the coconut tree, the animals, and so on. Right? So we test this publicly available data set. And here's basically the results. And we compare with the recovery Maya by reloading data from the disk. So essentially, what I show here is basically like the five small models we tried. On the y-axis basically shows that it's the time it takes to recover the Maya. So on for the blue bars, basically correspond to starting the Maya fresh by reloading the data from the disk. Right, from each model from the disk. And the yellow bars correspond to the time it takes to restart Maya directly from our snapshot. So the snapshot is, of course, is taken once after the Maya loads the data set, it will take a snapshot. And then if Maya crashes, we can restart from the snapshot. So you can see that it's basically, if you don't use our in-memory snapshot, it takes basically about up to 70 seconds to restart this bonsai A model. And with the zero-hour snapshot, it takes about 3.6 seconds just for the Maya to show up. So basically, the saving comes basically at least from two parts. First part is we don't need to load the data from the disk. Right, we directly recover from the memory. Second part is we don't actually have to let the Maya to reinterpret those data coming in. So they are already understood the data in the memory states. All right, so the states are already taken. So in the snapshot. So that's basically generated huge savings for this application. So let me continue with the other features. So with a snapshot, we also note that we also support some of the clustered applications. So what is the motivation of supporting cluster application, right? First of all, most of modern applications are running in cluster modes. Like, if you look at the in-memory databases, typically they are clustered. If you look at the training application, they're clustered, right? So how can we help with that? So with the snapshot, first of all, we found that actually in real use case, we found that with snapshot, we can actually help to mitigate, if we can instantaneously restore from the snapshot, those instantaneous restore can help to mitigate the very expensive network-based sync upon the node failure. So I will show an example in the next. Also, if there's a catastrophic failure, let's say you lose the whole rack, you lose the whole cluster, or you lose the storage actually, And if the backup is in the storage, and if you lose the storage, then you cannot basically recover the database. But we can actually, without this kind of condition, which of course rarely happens, but we can actually provide fast recovery for the whole cluster using our snapshot. So the particular use case I want to describe is basically is an instantaneous snapshot restart for the Hazelcast in-memory data grid cluster. So our friend from Hazelcast, Dale, will actually introduce more on the Hazelcast in details. But here, essentially, what we offer is that we call the Zero IO Snapshot Coordinator. So the coordinator basically can coordinate snapshots for the processes running on different hosts at the same time. Right, so that it can guarantee a consistent state for the cluster. And also when the snapshot is taken, and we can abstract the cluster, each individual snapshot generate for different process into a cluster mode. So basically you can see that this is the snapshot for that cluster, and this is the second snapshot for this cluster, and so on and so forth. And then we can also restore either a single node or restore all the nodes together. And basically the cluster will show the class basically can come back and start serving the user, just as a single node Redis use case. So here is basically some number I want to share. So in particular for Hazelcast, so the issues with the Hazelcast with large memory is that once you have you use lots of memory in the Hazelcast in those in-memory databases, and if there's a failure on some of the database nodes, so one thing will happen is that if a node fails, so the cluster manager will see that failure and will start triggering the repartition. Because the node is actually, one node is down, so the whole data distribution is according to a hash ring. So they have the hash ring structure changed, so they have to rehash things and repartition the data. So to the repartition basically triggers the data movement. You have to, so each node will start sending some new data to the other nodes to rebalancing the cluster. And just imagine you use if you have lots of memory used for each data node, then it will take very long time to finish the resyncing. And also, once you fix the failing node, right, bring the failing node back, so basically the cluster manager will see that a new node is joining the cluster. It also will trigger the rebalancing and repartition. And that also basically involves other nodes sending the updates, sending the data to the newly joined nodes, right? And that's also very expensive. So as a matter of fact, here the data shows here basically proves this point. So we measure the kind of 3 data points. So we let the memory per Hazelcast instance uses stores like 5 GB data, 10 GB, or 14 GB data independently. Right? So you can see that with more data used by the database, it takes longer upon a node crash. It takes much longer to do the data resyncing and the data repartition upon a node failure and upon the node restart. So it essentially means that if you want to do a recovery, you have to wait for if the node is failed, you have to wait for the resyncing, and when the node comes back, you have to wait for the resyncing to finish for that data to be complete. However, with our memory machine snapshot, essentially what we can do is that we can actually avoid the resyncing on node crash and avoid the resyncing on the node restart. Instead, we can directly actually restore the node or restore the cluster from snapshot. The format test basically will show that within less than 1 second, we can get the cluster back to the normal condition to start serving the users. So this is basically with a snapshot in memory, so we can actually avoid basically the resyncing, the copy of the data between the memories. Okay. So that's basically some major interesting use cases on this particular snapshot, the simple snapshot features, and there are also other snapshot related features here. For example, a snapshot we developed actually can be cloned. And so this allows instant cloning, the cloning of the application. This actually answers the raised question. So this allows the instant cloning of the application. And these applications actually can share the same memory in snapshots. So for example, let's say we have this snapshot, and you can first of all, you can definitely restore the snapshot, which will give you back the application. And also, meanwhile, you can actually clone the snapshot instantaneously. Also, these clones will spawn up instantaneously. And these clones will share the same memory footprint, same memory with the application until they are modified. So, and again, the modification is based on copy on writes. So the use case can basically include, if you want to spawn out the replicas of the huge in-memory database, you can do that through the snapshot. So for load balancing, we actually see such use cases in machine learning for those hyperscalers. And also, if you want to, let's say you want to test the database upgrades or do some other sandbox testing in your development environment, you can actually also use clone to clone your production databases and just to work on the clones to debug them. So the snapshot, once it's taken, as mentioned, you can actually, with our recent release, you can actually replicate the snapshot from one server to another server directly from memory, one server's memory to the other server's memory. So this basically provides high availability, basically to your in-memory snapshots, and also allows you to do the fast migration. So you don't have to basically copy the snapshot to export to a disk and import it back to the other servers through multiple copies. So essentially, for example, if you have an application, you can take a snapshot on server one, then with our software, we already support this kind of transfer, snapshot transfer, and you can actually stream that to different servers, and you can also then run the restore and clone for that snapshot on different server, and the application will come up. And for example, if you want to do an application migration, you can, once the clone comes up, you can basically kill the original applications. So we actually have a use case where we can show that we can actually migrate a multi-node Redis cluster to a different set of VMs using our cluster snapshots and the cluster snapshot replication features. And of course, finally, so we definitely support, because of memory is still a relatively more expensive resource, right? So if you have a very cold snapshot, you want to archive or backup, we also give you the feature that allows you to export the snapshot outside of the memory to a storage system. So this storage basically can be a shared storage, even can be the storage on the cloud S3, NFS or SAN, right? And you can then basically allows you to import the snapshot back from the storage back to a local, the memory of another server. And then you can basically do all the restore and the cloning operations on the imported snapshot.
So how does that work from an addressable standpoint? So it's at a certain address, you save it or you export it, and then you re-import it. How does the application then know where to find the imported addressable space?
Yeah, so we'll also recreate basically the virtual memory address space for the application, because during Snapshot, we also save those metadata for the application, like the sockets they are using, the virtual memory address space they are using, the file descriptor they are using, all the other handlers. And then when we restore, we actually first restore all these infrastructure, like the virtual memory address pages and so on. Then we basically use our snapshot, which lives in the physical memory, to back those virtual memory address spaces.
Okay, so the whole memory map is then also exported and then recreated at import time. Okay, exactly. Thank you.
Exactly.
What's the latency and the overhead of having to manage this many memory pointers?
Memory point. So you mean the latency for restore?
Well, just the overhead in general of having this layer in between.
So there are a couple of things. So for memory allocation, so there's some overhead for the memory allocation in the sense that we will redirect the memory allocation cost to our function cost, but those overhead is very, very small. I think we actually can show that for many applications, it's not really, it's very minimal. We don't see much difference between running application on ours and running application on normal DRAM.
Do you have any numbers to go behind the small or low?
So I think basically, tens or single-digit microsecond level for the memory allocation interception, which is very, very, very minimal. And also for snapshot. So again, for snapshot and restore, the snapshot takes about tens of milliseconds just for us to go over those memory pages that we want to persist. So yeah. It's about tens of milliseconds to 100 millisecond level. Yeah.
Okay.
Yeah.
Hey, sorry, one more question. and I'm definitely a storage noob here. But just sorting through this, I just want to be clear. When we're doing this kind of taking the primary snap, and it does say server one, but we're exporting that to potentially like object store somewhere else and then bringing it back. Does that always have to come back to the same machine, or I can use that to kind of clone across multiple machines and scale horizontally?
Yeah,
right?
so yeah, you can actually clone into, basically you can copy the snapshot to multiple machines, no problem. Yeah, multiple VMs, multiple machines, as long as the target machine has similar environment as the primary snapshots environment. Yeah.
Okay, so if I had like a fleet of identical machines, yeah, I could kind of create a model on one, snapshot that into memory, clone it across all of them, and kind of run different variations in that way.
Yes, you can. Yeah, exactly.
Interesting.
You can do it today, actually. Yeah. Okay.
So yeah, what's a typical ratio of DRAM to pre-mem kind of thing? Is it like 10%, or is it depending on the application?
Yeah, it's a good question. It's a really good question. So I would say, yeah, definitely it depends on applications. So some applications really doesn't, we see that really doesn't require lots of the DRAM there. So like, for example, actually we see that actually MySQL is actually such an example. You can do like 1/8 ratio, and you can still reach performance that are very similar to the DRAM performance. But for memory hungry applications, like full in-memory applications, that some like the in-memory databases, I think basically the memory ratios can be, DRAM PM ratio could be higher, like 1/4. So typically we test 1/4, 1/8 ratio, and sometimes for some very memory hungry, memory intensive application, we test like 1/1 ratios too.
I'm going to show this later, but can you show us what the actual implementation of this is like? What's the software, and how do you manage this as a person implementing this inside a business?
Oh, you mean something like a demo or something? Yeah, I think we can probably. That's actually I didn't prepare the live demo today, but I think maybe we can in a different session, or in the breakout session, we can show you maybe trying to show some demos there. Yeah. But I think meanwhile there's a lot of actually demo videos on YouTube. You can see that essentially we have a UI and we have a command line. So on the UI, so essentially you can once you launch applications, you can see that the application shows up in the UI monitoring dashboard and will show you how much memory you used, when did you start, what is the memory bandwidth, so on and so forth. And then next to the instance, the process, there's a button called snapshot. You can just click the snapshot and basically will generate snapshot, and the snapshot record will shows up in the dashboard. Or if you use CLI, essentially you're passing the process information and pass the PI process ID you want to snapshot, and we'll snapshot against that process. So this is my last slide. So essentially, I just want to give you a quick summary. So the memory machine basically just provides two major, two category of features. The first one is transparent memory service that supplies big memory to the modern applications. A second is also with the zero IO snapshot, basically guarantees that big memory is persistent instantaneously and make them highly available and performant again.
So one of the questions is, is the snapshot, application consistent or not? And I guess the question really resolves around when you bring up, let's say it's Redis memory database or something like that, sitting in the mem machine, and you snapshot it, and then something fails. You can go back to that snapshot. Do you have to roll it back to some prior transaction point, or is it consistent, I guess, at that point, that can just take off from that point?
It is, yeah. So when I take a snapshot, it is consistent at that point. So we don't need to ask the database to roll back the transaction and so on. Yeah, we just directly go to that memory state.
And so the advantage really is that you bring all the data into memory for this application, and you have the application itself in memory. So when you clone it or snapshotting, you're snapshotting everything associated with that application at that instant in time. Now it's going to miss anything since that time, since the last snapshot, but it will be consistent at that point and just can take off.
Correct. You're absolutely right. So the snapshot is basically a point in time. So it doesn't basically between the snapshot, the data change. We don't capture. Essentially, it's not like you cannot use the snapshot to replace the log. Essentially, right? So you have to, if you want to, let's say you crash in between the two snapshots. Right, then you have to only restore to the latest snapshot, and then you have to replay the log to catch up to bring you back to the latest states.
And the logs would be where in the source? It's certainly not on a disk because it can't keep up. It would have to be in some other memory space, right?
Yeah, so typically we just rely on the application itself to replay the logs. For example, we actually integrate with the Redis so that if the Redis fails, we can restore the Redis from our snapshot, and we can ask the Redis to replay the rest of the logs to recover to the latest states. Yeah, so and then of course the Redis stores that the log on a storage disk or file system.
Oh, okay.
Yeah.
Hugh, a couple questions on your snapshotting. Previously, historically, in copy on write, you had to pre-allocate capacity. Do you have to do that?
So for copy on write, I definitely. So when I do copy on write, it definitely introduces a capacity overhead. We have to basically essentially allocate a new page to hold those and copy the existing page that we are modifying to the new page, and then modify the data there. Right. So
and
that's.
Yeah, and so what's your limitation on the number of snapshots you can do in any given system? I'm sure it's memory constrained, but generally.
Yeah, so right now actually we have a configurable limit. So right now the limit is like 256 per process, but that one just can be modified. So we really don't. It's really limited by the memory resources that we have. Yeah. Right.
I think for AI workloads, you never have enough memory. Do you see in the near future crossing the 4 terabyte boundary?
Definitely, as I mentioned. So we are actually also have a thread studying the CXL and remote memory based on RDMA and CXL. So yeah, definitely that with that effort, that will bring the remote memory into memory machine. So you can actually allocate across the nodes.
Right. And when you talk to customers, are they more inclined to go to MemVerge because you can get, quote unquote, more memory, or are they reaching out to MemVerge because you have the ability to do memory and restore in a much faster fashion?
So I would say we have actually probably 50-50. We have actually a customer on both sides as well. So yeah, so some customer accounts for bigger memories, just for bigger memory, because for some application there is no need for this fast restore, and they just need more memory. And there are many interesting POCs that actually relate to the in-memory database, right? So the users actually goes with the user's snapshot. Yeah, so we have to it's very mixed and pretty balanced so far.
Yeah, and what are the typical use cases? Do you see more virtual machines or databases, applications? Any AI specific? I mean, my background is in AI, so I would say that snapshotting and checkpointing is really important, and the more the better, and the faster the better.
Yeah. So definitely, I think, as I mentioned, so with some larger memory, we can definitely allow the training, the users training with larger models, and also with a snapshot. Basically, the snapshot allows you to quickly, swap when you inference, when you do model serving, you can use a snapshot to quickly roll back to the model you want to you like the most, or you can roll back to different models to test the precision. And meanwhile, also my colleague Yong will introduce more use case on data analytics and the AI. That it also helps with you on the debugging. So say that you want to tune the parameter of a machine learning pipeline, right? And the machine learning, to tune that, it requires reloading lots of data and redo the computation. So what you can do is, after loading the data into the memory, you can take a snapshot of that point. Then you start doing the parameter tuning. If you are not satisfied with the current parameter, you can just simply restore the snapshot and retune again, so that you avoid those I/O time, repeating the I/O time and recomputation time of the previous stages.